Okay, so last time we studied the scattering in terms of electric and magnetic dipoles. So radiation fields of the electric and magnetic dipoles are treated as scattered fields. Now we are going to investigate the scattering as a general perturbation theory, and it will be the explanation of the blue sky. So basically we will write again the Maxwell's equations for the free medium. Del dot B is equal to 0, del dot D is 0, and curl of E is minus del B over del T, curl of H del D over del T. So suppose that we don't have free charge density and current density. So you can write a wave equation combining this in the following form. Laplacian of electric displacement mu 0 epsilon 0 del square over del T square with a non-homogeneous terms, but not non-homogeneous terms will be a physical meaning, so I will discuss. So suppose that the form is in this form: curl of D minus epsilon 0 E plus epsilon 0 del over del T curl of B minus mu 0 H. So actually these are the related with the polarization and magnetization. So basically we have a non-homogeneous wave equation. So in space there are some slight perturbations of the perturbations in the what polarization and magnetization. So incoming wave will scatter these perturbations. But first, indeed the right hand side is equal to the left hand side. We can show very easily using the Maxwell's equations. So take this term and write that term in the following manner. So epsilon 0 del over del T curl of B minus mu 0 epsilon 0 del over del T curl of H. So curl of H is nothing but del D over del T. This is curl of H. Acting of del over del T is del square del T square minus mu 0 epsilon 0. So we pick the one term. This is that term. So let us study the other terms. The other term could be written as epsilon 0 curl of del B over del T. Del B over del T is minus curl of E. So that term is nothing but epsilon 0 curl of E with a minus sign. And I said to you that this is the part of the wave equation here. So I am equating the left hand side and right hand side. And epsilon 0 minus epsilon 0 curl of E is equal to, is, what is this? This one minus plus curl of epsilon 0 E. So this term will cancel with that term. And the leftover term will be minus curl of D, and that is nothing but gradient of divergence of D minus Laplacian of D. So divergence of D is 0 because there is no free charge densities, and I think this is in that form. So we will obtain, so we have a minus sign, that should be in that form, multiply with minus. So we have Laplacian of D, and from here we have mu 0 epsilon 0 del square over del T square. So basically, left hand side are equivalent to the right hand side using the Maxwell's equations. But right hand side has an important meaning because this is the source term of wave equation or non-homogeneous part of the wave equation, and this term is related with the polarization, and if you play with that term with the units, that is related with magnetization, not exactly magnetization, but it is related with the magnetization. So basically, in space, a distribution of magnetization and polarizations, not a single scatter, only one. There are distributions of the scatters, and there's incoming wave, plane wave, and that will scatter from those distributions. Now, the next thing, how we can solve this? We can solve this very easily because we know that the solution of the non-homogeneous wave equation. So let us write the appropriate form of the del over del T and del square over del T. You know this. Del over del T will be replaced by minus I omega, and that will be replaced by what? That will be replaced minus I omega times minus I omega. That will be omega square, and divided by that will be minus omega square and times mu 0 epsilon 0, that is k square wave number, because mu 0 epsilon 0 is the 1 over c square. So left hand side is Laplacian plus k square acting on D, and right hand side minus curl of D minus epsilon 0 E and minus I epsilon 0 omega curl of B minus mu 0 H. If right hand side is 0, say you have some homogeneous solution D0. If there is no any scatters in the medium, you will have some D0, some solution, yes, tell. But if there is the source, the full solution will be some of these. And the solution of this is the convolution of the source with the Green's function and integrate through the whole space. That will be 1 over 4 pi d cube x prime Green's function times the source. So integral should be taken from the prime, therefore these operators should be depending on the primes. So curl of prime of curl of prime d minus epsilon 0 e so actually solution minus should be minus 1 over 4 pi times the source. Therefore this should be positive, then other should be positive, if you remember that the solution of the non-homogeneous wave equations. So that is nothing but plus I epsilon 0 omega curl of B minus mu 0 H. So let us continue. This term will be the electric displacement due to the scattering, and this part is the d0 if there is no any scattering in the homogeneous part of the wave equations, from the homogeneous part of the wave equations. Now let us study the x minus x prime again. So instead of x minus x prime magnitude, I can write r n dot x prime. If you say that x prime is the region of the scatters and x is somewhere else, and x has the magnitude r and direction is an unit vector as we did. So x minus x prime magnitude, using the binomial expansion, you can easily show that it is nothing but r minus n dot x prime. And here in the exponential that is the same. So in the exponential this little difference is important because it creates a phase shift. But here it's not important. R minus n dot x prime is approximately r. So basically you can take the e to the r over r terms outside the integral because it's not depending on the location of the sources. Then you can write that the d, let's say d scatter. Let us call all of them as a d scatter. In the following form, take the e to the k r over r outside. The integral. So the leftover terms is called a scattering amplitude. So if you take this e to the kr over r outside, the other part will be 1 over 4 pi. So we have to write it again. So that is nothing but d cubed x prime e to the ik n dot x prime curl of curl d minus epsilon 0 e plus I epsilon 0 omega curl of B minus mu 0 h, close the parenthesis and the big one. Probably I write the sign incorrectly because I take the e to the exponential to the IKR outside, and the leftover term is minus, and therefore this should be minus. So again, the scattered electric displacement due to the spatial uniform distributions of the magnetization and the polarized sources has the form of spherical wave and a vectorial part. That vectorial part is called a scattering amplitude. It's vector. The name is scattering amplitude, it's vector. Denoted by A sub scattering. So that is called scattering amplitude. Okay. So we will put the scattering amplitude more easy format, and then we will do application for the scattering from a dielectric sphere, and also if we have a random scatters in the medium like molecules in the atmosphere, air molecules. So basically D and E and H should be in exponential, and we can replace the curl operator with the IK cross. So let us do this. So let us replace the curl operator with IK n hat cross. So the scattering amplitude then will be in the following form: 1 over 4 pi d cube x prime e to the minus ik and that x prime. So instead of all curls, substitute ik n cross. So that will be ik n cross d minus epsilon 0 e plus I omega epsilon 0 ik n cross b minus mu 0 h, close the parenthesis. So I and I will be minus, I and I will make minus, and since it is minus, switch the one cross product order, make one more minus and make it positive. And here you have k and k square, and take the k square outside because k square is important, because in the scattering cross section the scattering cross section goes with the k to the 4th power. So let us take the k square outside in a common parenthesis. K square over 4 pi d cube x prime e to the minus ik and that x prime, and the rest will be what? This should be minus, switch the cross product order and write in that form: n cross d minus epsilon 0 e cross n, and this will be minus. If you take the k square parenthesis, that will be epsilon 0 omega over k n cross b minus mu 0 h. So this is the scattering amplitude. If this is the scattering amplitude, what is the scattered electric field? Electric displacement, that is nothing but e to the ikr over r times scattering amplitude. So let us talk again what are these things. So basically d minus epsilon 0 E is directly definition of the polarization, because you know that electric displacement is equal to epsilon 0 E plus polarization. Okay, you know this. This is directly related. The other also, but you have to play with the units a little bit. This is the polarization. If you look at the other term, do the following things. So I'll quickly play with the units. So say epsilon 0, omega over k is equal to what? C multiplied by C divided by C. That will be C square over C. And that is n cross B minus mu 0 H. And what is C square? That is square root of 1 over epsilon 0 mu 0. So this is nothing but epsilon 0 mu 0 1 over C. This will be cancelled. If you distribute the mu 0 inside, what you are going to obtain? This will be mu 0 and that will be H. So I write this why? Because this is what? Do you remember this? This is the definition of the magnetization. So this B over mu 0 minus H is nothing but the magnetization. So basically H is equal to B over mu 0 plus magnetization. So you saw this also from the first part and the undergraduate. So basically, this integral scattering amplitude times the spherical wave term, that is the scattered electric displacement, is related with the distribution of the polarization and magnetization in the medium. Now let us give a pause in a minute and look at what we did when we studied the scattered field in terms of the dipoles. Remember, a single dipole. What was the formula? So I have to find and write it. Yes, this is the formula. What was the formula? So that was the formula. If you have a single electric dipole and magnetic dipole, scattered fields are treated as a radiation from the dipoles, and the formula for the E scattered was the following: 1 over 4 pi epsilon 0 k square e to the I k r over r n cross p cross n minus n cross m over c. So this was the formula. Now look at whether they are similar or not. So we have the spherical wave term, we have the k square. Take the epsilon 0 there, that will be electric displacement naturally. Look at here, n cross p. N cross p is the electric dipole moment. Here, if this is the polarization, we have n cross p. But if you integrate this, that is nothing but through the volume, that will be polarization. And the other term is minus 1 over c n cross magnetization. If you integrate through the volume, that will be magnetic dipole moment, and here you have this one. So it is 1 to 1 is the same. But additional information here, this is a distribution of the polarization and magnetization. And one other additional thing is this. What is this? N is the direction after the scattering. X prime is the source regions here. Okay. If we integrate this for a distribution of sources, this will handle the what? Diffraction or interference effects. Okay. If you have one single source of the electric dipole and magnetic dipole, you can represent this is a delta function and delta function at x prime is equal to 0, for example. If you integrate this, the integral of the delta function is easy. You will put 0 here if you put the source at the origin. So that will be 0, and this will be electric dipole and magnetic dipole, and you will get exactly the same form. But here, what is missing? The interference and diffraction. For single source, there is no. But if you have several distribution of the sources, the interference and diffraction effects are important, and this is handling this. Okay. Now, the next thing, I'm going to write that the scattering cross-section per salt angle, and then I will assume that there are scatters in the mediums, and they are like a perturbation. That means that the variation in the dielectric constant and the magnetic permeability is not strong, but it's distributed to some variation. And we will try to find that the scattering cross-section per salt angle. So the name of the approximation will be Born approximation. You know that the Born approximation in the quantum mechanics. This is the classical version in electromagnetic theory. That will be. So let us write that the scattering cross-section per salt angle. So if you remember that there was 1 over z2 z0, 1 over 2 z0, they will cancel. Even I don't need to put there. And r square, polarization after the scattering, that scattered electric field. Instead of this, I am writing the electric displacement because I will divide that the electric displacement square. Okay. This is the unscattered incident electric displacement. This is the scattered electric displacement. If you write in electric fields, that is easy because write this as a epsilon E, epsilons will be cancelled out. Okay. So this is the form of the scattering cross-section per salt angle. So let us. Oh, what happened to the? There's some. Okay, that is equal to what? Okay, that is equal to what? It's okay, but it's not sufficient. So what I wrote here, scattering electric displacement is e to the kr over r times the scattering amplitude. If you take this and put it there, what you are going to obtain? Absolute value of this, and e to the ikr absolute value will be 1, and the square, absolute value square, that will be 1 over r square. This is equivalent to what? Polarization after the scattering, that product with the scattering amplitude square divided by d0. You can write it in this form also. Now, let us keep this equation in the original format. We will need and erase the above. And let us distribute the scatters to the medium and put this equation in more easy format. So next thing is the Born approximation. So suppose that position dependent electric displacement is nothing but epsilon 0 times the electric field plus some perturbation in the medium, and that perturbation could be introduced as variation in the dielectric constant as a function of x. Okay, so there are some fluctuations in what? Dielectric constant in the medium. Medium is not uniform. Okay, it's changing a little bit. Dielectric constant is changing a little bit. Therefore, electric displacement is changing. And B field, Bx, is mu 0 times h of x plus some variation in the magnetic permeability in the medium. You can write this. Okay, and these are first order terms. The squares of this are not important, so there are some little variations. What I needed here in the scattering amplitude, I needed d minus epsilon 0h and b minus mu 0h. So I can write this in the following form easily. That is equal to d minus epsilon 0e. Take this to the other side. That will be equal to variation in the dielectric constant times electric field multiply by epsilon 0 divided by epsilon 0. This term will be electric displacement d0. So d minus epsilon 0, which we will need to put here later, is nothing but variation in the electric displacement, which depends on the location, position with respect to the epsilon 0. You can do the same thing to the below one. Then b minus mu 0h will be what? Variation in the magnetic permeability over mu 0 times h. HB. B incident. B is equal to mu 0h, and mu 0s will be cancelled, and they are the same equations. So what are the B0 and D0? They are nothing but the incoming fields in the incoming components of the electric and magnetic field of the incoming plane waves. So D0 is some polarization of the incident wave. We can call epsilon 0 unit vector, amplitude of the oscillation, and propagation direction I, k, and 0 dot x. So k0 head and n0 head parallel to each other. They are the same unit vectors. So here this represents the source-free region, the incoming waves propagating, and there are some scatters here, which variations of delta epsilon and delta mu. So then B0 simply will be impedance of the free space. I think it's inverse of the impedance. N0 cross D0, and D0 is above. So these are the components of the incoming fields. So what we have to do, we should pull off this and plug inside d minus epsilon 0 h, b minus mu 0 h. So next job is to do this calculation. This one is easy, this one is more tricky. So let me do for this one. So you have the scattering amplitude. Instead of d minus epsilon 0 e, write delta epsilon, which depends on x prime, over epsilon 0 times d0. d0 is what? d0 is incident polarization of the wave, amplitude of the oscillation, e to the I k n 0 dot x. Okay. So at this point, we will come to this later on. Look at here. So that should be prime, of course. You have I k n 0. You have minus I k n. If you take the x prime parenthesis, that will be what? K n minus n 0. Do you remember that the k n minus n 0 in the exponential, that was a structure factor. Now it's coming naturally. Okay, it is coming to our calculations. The structure factor is coming naturally. So this part is more tricky, easy, but taking space. Let me try to work on here. So let me work on up. That one is equal to b minus mu 0 h is nothing but variation is the magnetic permeability on the space over mu 0 times b0. What is b0? Square root of mu 0 epsilon 0 and 0 cross d0. Cross d0. d0 is what? What is the d0? Polarization, incident polarization, d0 amplitude, e to the I k and 0 dot k, x prime. And what is the other terms here? I have cross product with n, epsilon 0 omega over k. Now I should do one more thing. So let us play with the coefficients, then do one more thing. What are the coefficients? Omega over k is what? C. C is 1 over square root of mu 0 epsilon 0. That is omega over k. You have epsilon 0. Is there a cancellations? There should be. What are these? This square root of mu 0 and this one cancel. And that epsilon 0 over square root of epsilon 0 is square root of epsilon 0. That will be cancelled also. It only coefficient is the del mu over mu 0. You have then n 0 cross epsilon 0. And you have n cross. So if you are comfortable about this region, I'm going to raise the up. Okay? Any question about the above region? Above part? Okay. So this is a form of the scattering amplitude. For the scattering cross-section per salt angle, I need the Dot product of the polarization after the scattering with the scattering amplitude and the square. That is the important term. So let me write this. Epsilon complex conjugate dot scattering amplitude over d0. Let me write this, then I can take the absolute square. So I will plug this there. So I have k square over 4 pi. 1 over d0 amplitude of the oscillation. But we have d0 here and d0 here. That will cancel. Okay, all d0s will be cancelled. So you have amplitude of the oscillation here, amplitude of the oscillation, that will be cancelled. And d cube x prime, you have e to the ik n0 dot x prime, e to the ik n0 dot x prime, and you have minus e to the ik n dot x prime. So that is nothing but e to the ik n0 dot x prime. So that defines that the difference of the wave number direction before the scattering and after the scattering. N0k is the incident direction and k is the direction after the scattering. And that is in the parentheses, so this should be prime. And I need to calculate the epsilon complex conjugate dot as. In the first term, you have epsilon 0. So for the first term, you will have what? Variation in the dielectric constant over epsilon 0. And the other term will be the epsilon complex conjugate dot polarization after the scattering dot epsilon 0. Do you remember this term? We use this. For the other term, we have minus sign. Then variation in the magnetic permeability over mu 0. And I have what? I have what? N cross N0 cross epsilon 0, and this vector should be dotted with epsilon complex conjugate. Epsilon complex conjugate. And close the big parentheses. This is the form. But here I have a mistake because I forget to write that the n crosses. So above we have a mistake. We will come to that result, but we have a mistake at this point. So let us correct that part. So this epsilon complex conjugate dotted with what? Epsilon complex conjugate dotted with what? N cross epsilon 0 cross n. So that will be n cross epsilon 0 cross n. So make a correction here. So we have n cross epsilon 0 cross n, and if you take the dot product with the epsilon complex conjugate, you can write this in that format: epsilon 0 complex conjugate dot n cross epsilon 0 cross n. But we will see that this is equivalent to the epsilon complex conjugate dot epsilon 0. So quickly we can see this. So let us say this is again 1, and let us call this is 2. So I think everything is correct now. So let us evaluate this cross products with dotted terms. So that first term will be what? The first term is epsilon complex conjugate dot n cross epsilon 0 cross n. That is equal to epsilon complex conjugate dot this double cross product, that is nothing but n dot n epsilon 0 a dot c along b, if you say a, b, c, these vectors, and the other term minus n dot epsilon 0 along n. This is unity, and epsilon complex conjugate at epsilon 0 is the term which I wrote without calculating here, there. And what is the other term? N dot epsilon 0 epsilon complex conjugate dot n. What is the meaning of epsilon complex conjugate dot n? Epsilon complex conjugate is the polarization after the scattering, and is the propagation after the scattering. That is mutually orthogonal to each other. This is 0. And you end up with that term. This is equal to epsilon complex conjugate dot epsilon 0, which we use this again in the scattering of the electric dipole. So let us work on to the second term. The second term is epsilon complex conjugate dot n cross n0 cross epsilon 0 unit vector. And if you call this is the vector A, B, and C, this is the volume, and it is A dot B cross C, and that is equal to A cross B dot C, and that is nothing but epsilon complex conjugate cross n dot n0 cross epsilon 0. That is the other term. So this, the other term, is nothing but epsilon complex conjugate cross n and n0 cross epsilon 0. So this is the form of the epsilon dot scattering amplitude. If you take the absolute square, you can calculate the scattering cross section per solid angle. Now the next thing, we will have two examples. One, in order to confirm this result, we will look at the scattering from the dielectric sphere. We have to find that the scattering from a electric dielectric sphere as we did from the radiation approximation. And the second, if we have many scatters here, like air molecules, and how will be the scattering cross-section per Salt angle, and that will be explanation of the blue sky. So let us give a break, then we can continue.